just mention, again, scheduling sorts of things. All right, so I turned on the recording. I'll mention the test because I'm not quite through grading it, but it's close. So so I'll be sending that back to y'all soon, but I'll say more about that in just a second. On the homework, we do have homework due this evening. So this very short homework that I was hoping you would get a chance to look at it before the test, but if not, then it's due this evening. It's very short. It's only 3 questions, although I think the questions have multiple parts, but there's no computations involved. It's just interpretation sorts of questions, and they're multiple choice questions. So it's easy to finish, and I can see from the scores of people who have done it that it's easy because the median score is like 100. So most people are finding that one really simple. So that should be easy to complete for the remainder of you if you haven't done it already by this evening. Okay. All right. So and then I still have this one. This one is going to be more challenging now. I still have this one listed as Thursday. So this is computing derivatives using the limit definition. We're going to look at 1 or 2 more examples of that today. And then you'll be on your own in working on these homework. So this one's going to be harder because it involves more algebra. And then today we're going to learn about how to short circuit shortcuts we can use to find derivative functions, instantaneous rate of change functions, without having to go through the limit definition. So you'll find this homework a great relief, okay, because we'll be able to find formulas for derivatives without having to go through this complicated limit process. All right. So that's going to make the differentiation process a lot simpler. So that'll be a great time saver for us. Okay, but we have to do a little bit of a couple more examples of finding derivatives the hard way before we start looking at finding derivatives the easy way. So that's what's coming up. So immediately on your radar here is just finishing this work for tonight. So that should be fast. All right, so on the test, so can't say much about the test because I'm still in the process of grading it, but I'm more than halfway done. So that will be finished by tomorrow. So when that's finished, I will post the grades in WebAssign, and then I will email you your graded test back to you, right? Okay, I'm going to reply to the email you sent me with the test. So I hope that's the right email, because I'm just going to reply and attach the graded test to it. And your score will be in the test, of course, but it'll be also posted on WebAssign as well. Now, one thing about the grading is, I'm grading these on the computer and just typing in, if I'm deducting points or comments, but that's not easy to do. So don't expect a lot of corrections or comments. There will be some on your test, but I can't add a lot. So so you need to really look at the answer key, right, to the test, and review that along with your test when you get the test back. So you're the one that need to fill in, what the correct answers were on your test, right, from the answer key. So that's really important. So make sure you do that once you get your test back to correct whatever mistakes that you have, right? Because again, I just can't, if I were writing, it would be easier for me to add more comments, but when I'm typing, that's hard to do, especially if I'm trying to type in math notation. That's really hard to do. So, all right, so you'll be getting that back. Now, one thing I've noticed is what would have helped, okay? And so, so for test number 2, be sure now that you attend Madison's test review for test number 2. So no one went to that this time, and that would have greatly benefited a lot of people, okay? So, because, but this is always the case. People miss questions that were really easy questions, and had they gone to, for instance, the test review or looked more carefully at the review that I gave, right, then they wouldn't have missed those easy questions. So you're going to be sort of kicking yourself when you see the answers to some of them. You're going to say, oh yeah, that was simple. Why did I miss that? And that was because you just had not prepared enough by either looking at the test review carefully or going to Madison's SI session. So when it comes around to test number 2, you don't want to make that sort of mistake twice, right? You want to make sure that you've looked at the test review carefully, and you want to make sure that you've gone to Madison's review session, if at all possible. If you can't make it to Madison's review session, then try to make an appointment with a tutor in the math center, an online appointment with a tutor in the math center, right? And have them help you go over the parts of the review that you find confusing, right? Okay, so that's just my comment before I before I send the test back. Okay, see if there's anything else I want to say in that respect. I don't think so. Now, another thing I have to add to WebAssign is your class participation grade, and that take me a little bit longer. For most of you, that's going to be 100, but that will take me a little bit longer to put that into WebAssign. So that will be coming eventually into WebAssign. Remember, you get a class participation grade along with every test. It's not part of the test, but I'll add that to WebAssign, so you'll have another grade in WebAssign. Someone have a question there about anything? So so that's kind of so that's just where we are for the time being. All right, so we're coming up on spring break shortly, right? Next week will be spring break, so that'll be nice. We'll get another week off, like but hopefully not as cold as the last time we were off for a week. Okay. All right, so if there aren't any particular questions, I'm going to just go into the notes, and then we're just going to pick up where we were last Thursday with the notes, if y'all don't want to ask me anything. So again, remember, this homework is going to be due tonight. Okay, so let me pull up the notes then, and see if I got the right one. Yeah. All right. So again, what we're finding now are what are known as derivative functions or instantaneous rate of change functions. So these are actually formulas now, like the formula for the function itself, the original function, but with a rate of change function or a derivative function. What the output from that derivative function gives you is the instantaneous rate of change at a particular point on the graph of the original function, right? Okay, so the purpose of the derivative function is to give you a formula that will make it easy for you to calculate what an instantaneous rate of change is for a given function, right? Okay, so it's a formula that formula produces instantaneous rates of change for a given function. All right, and so we don't have to go through this terrible process, right, of trying to find tangent lines by drawing them or by zooming in on the graph of a function, right? We'll just have a formula that we can use to compute slopes of tangent lines without actually having to draw the tangent line in some way. Okay, so let's take a look at an applied example. And in this example, I'm never going to look at a graph. So we're going to be answering what are kind of geometric questions. A rate of change is kind of a geometric question because it kind of relates to, if a function is increasing, or doesn't kind of, it relates to if a function is increasing or if a curve is increasing or decreasing or not, right? It relates to, what the tangent line looks like at a particular point on the curve. So those are sorts of geometric questions, but we're not going to ever look at the graph of this particular function. We're going to sort of do all this geometry just on paper, okay, without actually imagining, even if we don't need to, what the graph even looks like. All right, so here's this kind of a basic physics type question. So it says at time t equals 0 seconds. So so we're using elapsed time here in this example. A diver jumps from a diving board, of course. So the diver's gonna, go up into the air a little way and then, of course, fall into the water, right? And so it says the position y of the diver in feet above the ground is given by the following function. Okay, so this is just a function from well-known function from physics. All right, and so the y here is the height of the diver. I guess we're introducing function notation here just to give a name to this function. So the name of this function is s of t, and here's the formula. Now I have to explain the formula a little bit, but notice the input variable to the formula is elapsed time, right? Because the diver's height is changing with respect to time, right? Okay, so the input quantity here is elapsed time after the diver jumps off of the diving board. So we have minus 16t squared plus v sub 0 times t. So we're going to fill in a value for v sub 0. That's not a variable in the problem. And then plus a constant here, s sub 0, and we're going to fill in a value for this as well. Okay, this value v sub 0 that's multiplied by t, this is what the initial velocity of the diver is. Okay, so so we'll fill in here. We'll make an assumption here in a moment about what the initial velocity of the diver is. That is the initial velocity when the diver jumps off the diving board, right? Okay. Now, of course, the velocities, the diver's velocity is going to be changing over time due to the effects of gravity, right? But v sub 0 is the initial velocity. This is going to be in feet per second. And then s sub 0, this is the initial height of the diver. Okay, so this is sort of the height of the diving board, right? This is the height that the diver is jumping from. So if you're in different diving situations, this quantity might change, the initial velocity might change, and the initial height might change as well. Actually, there's nothing special about a diver in this formula. This same formula would apply to any object falling under the Earth's gravity. Okay, so you could make up a story about any object being tossed from a height, and you could use the same formula, right? We're going to assume that for our diver, the initial velocity is 16. Notice that's positive. It's 16 feet per second because this is a velocity, right? But it's positive. So that means that, as you would sort of expect, right? Initially, the diver is going to go up, right? Okay, so the diver's jumping up or is, springing up, right? If it's a springboard. So the diver is going up initially, right? Okay, and of course is going to reach a maximum height and then is going to drop back down into the water, right? But it's important to notice that this is positive. So at first the diver is going up, and then the diver could be a she. The diver's initial height is 32. So the height of the diving board is 32. Okay. All right. So obviously we want to answer questions here about, how fast the diver was going at a particular instant, right? What the diver's velocity is. We know at the beginning it was 16 feet per second, but that's going to change. And then, questions about, things we can answer about, when does the diver hit the water and other things like that, right? Sort of any question we could think to ask about the diver that we can derive from this height function. All right, so we better fill in here the actual height function, right? So let me change my position here a little bit because I got to put in the right initial velocity and right initial height, right? So we have minus 16 t squared, and then plus that initial velocity, which is 16 times t, right? And then plus the initial height of 32. So there's the actual formula for this particular, situation. So the very first question is sort of the basic a differential calculus question. It says use the limit definition because that's the only really mechanism we have at the moment, to find the formula for the derivative. Here, I express the derivative in old-fashioned notation, dy over dt. That means derivative, okay? dy, because y is our, that's the height, that's the output variable in this function, and t there is our input variable, right? That's elapsed time. But this means the same as writing s prime of t, okay? All right, so this is the old-fashioned notation. That's the more modern notation, but they both mean the same thing. That's the instantaneous rate of change function. That's the formula we want to find, right? That will tell us the rate of change of that diver, which is kind of the velocity of that diver, right? At any time, not just the initial velocity, but at any number of seconds after the diver has jumped off the diving board, I guess until the time the diver hits the water, right? All right, so so what limit now do we use to find this rate of change function? Remember, it's the limit as the increment goes to 0, right? Of, and then you just have this fraction, which is really just an average rate of change calculation, right? So you have s of t plus h, right? You take your input variable plus the increment, apply your function to that, minus s of t. So you're just subtracting off your original function. And then remember, you divide that by the t plus h minus t, right? Which of course always simplifies to h in this calculation. All right, so so you've got to get this written down correctly to get started. But now, Melissa, there's going to be some algebra. Okay, all right. So if you're dreading the algebra, well, here's the point where you know, where you're going to encounter the algebra, because we have to actually calculate now. We have to actually now simplify this expression, which involves computations with some variables, right? When you do computation with variables, that is what algebra is, right? So let's bite the bullet. Now, some of the calculations, though, are easy. So there's really not much work to do. Of course, the denominator is going to simplify to h, so that's easy. And then s of t, there's no work to do here because you know what the formula for s of t is, right? It's just the minus 16t squared plus 16t plus 32. So this you can fill in very easily, but be careful that you, when you fill in that minus s of t, be sure you put it in parentheses, because you have to subtract all of s of t, and s of t has 3 terms in it. So I'm going to put minus, that this minus sign is the same as this one, and then in parentheses, I'm going to put the formula for s of t, which is minus 16t squared plus 16t plus 32. So on the next test, whenever we come up to that, and you will have to find a derivative, at least one, using this old-fashioned limit definition. You're going to find it really tedious at the point of the second test, because we're going to learn a lot of shortcut rules for finding derivatives where we don't have to go through this limit process. But you'll still have to have at least one problem on the test where you have to do it the long way. And this is the mistake you're going to make most frequently. You're going to put minus and then this function here, and you're going to forget to put the formula in parentheses, and you're going to make a sign mistake. And when you make that sign mistake, it screws everything up. So everything will just go off from that point on. All right, now, okay, so this all of this was kind of easy. Here's the hard part. We have to calculate s of t plus h, right? So I have to fill in t plus h into this formula. Now, if you want to, you can do that right here as part of your limit calculation, but I'm going to be a little bit careful, and let's do that off to the side if I can find some room. So let me scroll way back up here, and up here I'm going to calculate s of t plus h. So what is s of t plus h? Well, that's minus 16 times t plus h squared So you're going to substitute t plus h for t, right, in this formula. So you have minus 16 times t plus h squared plus 16. See, that's a 16 times t plus h, and then plus 32. And now I have to simplify that. The only hard part in simplifying that is squaring the t plus h. So remember, when you square t plus h, right, that means you multiply it times itself. So once you've done this a couple of times on the homework, you'll get really good at it. But t plus h squared is t plus h times t plus h, which is t squared plus, and then you're going to have t times h twice. So I'm going to go ahead and just write it down quickly twice. That's 2 times h times t. See, t times t is t squared, h times t, and then you have h times t again. So that's going to be 2 times h times t, and then plus h times h is h squared. So all of that was t plus h squared. That's all multiplied by minus 16. So you have minus 16 times t squared plus 2ht plus h squared, and then 16 times t plus h. That's pretty easy. That's 16t plus 16h, and then plus 32. The only thing left you have to do here now is multiply in the minus 16. So you get minus 16 times t squared, and then minus 16 times 2 is minus 32. So you have minus 32h times t, and then minus 16 times h squared. So that's minus 16h squared plus 16t plus 16h plus 32. So that's a lot of terms there, but just be patient with all of those terms when you're simplifying this limit. All right, now let's come in and fill in all of this. So I just need to recopy all of this down here, right? So I have minus 16t squared minus 32h times t minus 16 h squared plus 16 times t plus 16 times h plus 32, right? And then you're going to subtract what was in parentheses. So that's just changing all the signs. So I have plus 16t squared minus 16t minus 32. All of that over the h. Now, at this point, guys, when you're working on your homework and you're finding these derivatives by using this limit process, again, it's going to be a little bit painful because you have to go through all of this. But at this point, this is where things get easy, because this is where stuff should start canceling. So do we get cancellations here? Oh, I think so. Notice that this minus 16t squared and this plus 16 t squared go away. Here you have plus 16t, and here you have minus 16t. So that goes away. And here you have plus 32, and here you have minus 32. So notice that 6 terms are going to cancel. So we have minus 32h times t minus 16h squared. What's left? Plus 16h. And then these terms are all gone. And all of this is divided by h. But now things get even better, because notice this h will divide into every term in the numerator. So that means you can divide it out. So you can divide this h into this one, it divides out. You can divide this h into this h squared, and the h squared goes away. And then you can divide this h into this h, and this one will divide out. So what's left? You just get minus 32t minus 16h plus 16. That's the end of the algebra. So we finished the algebra. And now we're going to finish the calculus, because the calculus part is now I have to imagine what's going to happen to this quantity. What's going to happen to this quantity when h gets really small? So someone tell me, that should be easy. What happens to that expression when h goes to 0? What are you left with? Let me see who's, wait, hang on a minute. Let me see who's here that I need to ask a question of. Not sure anybody from my list is here, though. Only Avery. Avery, you should hang around after the lecture because I need to talk with you. But Avery, when h goes to 0, when h gets really, really small, what's happening to this quantity? What's happening here when h gets really, really small? What's left of this expression? Are you there, Avery? No, Avery. Okay. All right. So that's not a surprise. All right. So who else wants to answer for me here? So what happens to this expression when h gets really small?
You're left with negative 32t plus 16.
What? Who's talking there? Yeah, Donna, what's left there?
You're just left with negative 32t plus 16.
Yeah, you're just left with minus 32t plus 16, right? Okay, so because this term is going to disappear, right, when h gets really, really small. So this is all that's left. That's it. There is your, that's exactly what we're looking for. There is the formula for the derivative. So you can call that again s prime of t, like we did up here, or you can call that dy over dt. So that's the formula that we can use now to calculate the instantaneous rate of change at any value of t whatsoever. All we have to do is plug it into this formula, and we'll know what the instantaneous rate of change is going to be. Or we'll also know what the slope of the tangent line is going to be, okay? Because that's the same as the instantaneous rate of change. So now see, by making a little bit of a sacrifice here and going through this algebra and to develop this formula, now we don't have to worry about tangent lines anymore, okay? Or any complicated process like that. Now we can find an instantaneous rate of change just by using this formula. So it's worth the price in that sense, okay? Because now we can easily calculate for this function, we can easily calculate instantaneous rates of change. So there's the very first question we're asked there, s prime of 1. So what's s prime of 1 going to be? So easy. It's just minus 32 times 1 plus 16, which is minus 16, okay? So what does that minus 16 mean to us? Let's interpret that, okay? Let's also write our interpretation of that. So what's s prime of 1 actually telling us about this diver? I'm getting ready to start over again. So Daniel, I know you're here, okay? Daniel, all right. So can you help me here with this one? What is the fact there that s prime of 1 is minus 16? Daniel Adego, I mean, okay? So I'll get to you, Daniel Gonzalez, in a second here. So Daniel Adego, what does it mean there, the fact that s prime of 1 is minus 16? What is that, what's that telling me? So what's that number minus 16 mean to me? Can you give me an interpretation of that? think about our interpretations of instantaneous rate of change, right? Remember, instantaneous rate of change is a slope of a tangent line. So it's the slope interpretation that, you know, that what informs us here. Let me ask it even simpler for you, Daniel. Is the after 1 second, is the diver going up still, or is the diver coming down to the water? So remember, initially the diver was going up because the initial velocity was positive 16 feet per second, right? So what's happening after 1 second?
The diver going down?
Yeah, the diver's going down. Well, what's your clue there that the diver is going down?
Negative 16?
The negative, right? It's the negative, yeah. So see, we know already that the diver's height is decreasing, right? The diver's height is decreasing because this quantity is negative, right? So we know already after 1 second, the diver has reached the maximum height and is already coming down again. All right, now Daniel, so let's take that a little bit further. We know the diver is coming down, right? Okay, so let's see if we can expand our definition a little bit. So after 1 second, right? After 1 second, because that's what we're dealing with here, right? We're dealing with the rate of change after 1 second, right? The diver's height, or in other words, the diver, I guess, is that height increasing or decreasing, Daniel? You just told me.
Decreasing.
Now? Decreasing, right. The diver's height is decreasing by, and how fast, Daniel, is the diver's height decreasing?
16.
16, right. 16 watts, though. We need a unit of measure.
I don't know. I think if inch or feet.
Yeah, do you remember what the height was measured in originally? I don't think inches doesn't make sense, right? So what?
16 feet.
Yeah, 16 feet, right? But this is a rate. So it's 16 feet per something.
Per second.
Per second, right, yeah. So that's what the minus 16 is telling us, all right? After 1 second, that's how fast the diver is falling, right? The diver's height is decreasing by 16 feet per second, okay?
Why is it only after 1 second? Why doesn't it start at the 0 seconds? Is it because
it does start at 0 seconds, Donna, but I just asked the question for 1 second. You already knew, by the way, what S prime of 0 was, okay? Without even using the formula, although we could get it from the formula too. But we were told what this was. Do you remember at the beginning of the problem, we were told what? We were told initially how fast was the diver going? The initial velocity was 16, okay? So you know that S prime of 0 was 16 because you were given that at the start of the problem. So when the diver originally jumped, Donna, his height was increasing by 16 feet per second. He jumped up, but after 1 second, he's already falling, okay? Gotcha. That makes sense?
Yeah, that does make sense.
By the way, that 16 also comes out of the formula because your formula is minus 32t plus 16, right? If you plug 0 into this formula, you still get 16, you see, okay? You get minus 32 times 0 plus 16. So you get it both ways, 16. Yeah, so at 0 seconds, initially, the diver's height is increasing by 16 feet per second. So between initially and 1 second, what has happened to the diver?
His direction changed.
His direction has changed. That's right. So the diver has reached, I don't know if y'all can see my hand or not, but the diver has reached the maximum height. I keep saying he, but it could be she. The diver has reached the maximum height and now is dropping. Okay.
Mhm.
Well, actually, that brings up a question then. At what time then was the diver's height maximum? So when did the diver reach the maximum height? Okay. So when did that diver reach the maximum height? By the way, if you take your formula, your original formula, not the rate of change formula, but if you take your original formula and set that to 0, that's going to give you minus 16 t squared plus 16 t plus 32 equals 0. If you solve that equation, what will you be discovering? So notice I don't have a prime here. I just have the original function equals 0. Here's the original function. Set that to 0. If you solve that equation for t, what will you be discovering?
You're probably gonna get more than one value for t.
Yeah, you're probably going to get more than one value for t, but that value for t that you get, Donna, what will that be telling you? It will be telling you what? You'll know the time when, what's the output here from this?
What the time when his height was 0?
Right, the time when the diver's height is 0. In other words, when the diver hits the water, okay? So if you take the original formula and set it to 0, you'll figure out when the diver hits the water, all right? But notice that's not quite what this, that's kind of the opposite of what this question is asking. This question is asking, when will the diver be at the maximum height, right? Okay, so if we set this to 0 and solve, we'll find when the diver's height is 0, but we want to know at what time was the diver's height the maximum. So you know it's between 0 and 1 second, right? Because after 1 second, the diver has already reached the maximum height and is falling again. Okay, so we know the answer here is between 0 and 1. But how do we figure it out exactly? So this is where calculus can help us. All right. So think about when you are jumping up, and if you've ever dived, okay, but if you've ever tossed an object up into the air, right, you'll observe the same thing, okay. When the object reaches its maximum height, right, okay, think about an object going up. It goes up, it's slowing down, it's slowing down, it's slowing down. It reaches the maximum height, right? And there's a very brief instance there when it pauses, correct? And then it comes back down again, right? So what's happening at that tiny instant when it's pausing? What is its rate at that time when it pauses at its maximum height?
0?
What is its rate of change? What is its velocity there?
0?
What? Say it loudly.
0.
Yeah, Daniel, what? When you
0.
throw an object up and you watch it go up and then it comes back down, right? It slows down as it's going up, and then when it reaches the highest point, it for just a very brief instant there, right? It pauses and then it starts falling. So at that very brief instant when it reaches its maximum height, what is its velocity there?
0.
0, right? Okay, because its velocity is changing from positive, right, to negative, correct, right? Its rate of change is switching from the rate of change is switching from positive to negative. It's going up and then it's going down. So how can we answer this question? Same thing's going to happen to the diver here, right? When the diver reaches the maximum height, there's going to be that very brief instant, right, at the maximum height where the diver's velocity is what?
0.
0, right. What formula gives us the velocity? That's the rate of change function, right? That's this function here, okay? So to know when the velocity is 0, we take this formula and do what? We take this formula and do what?
Make it equal to 0.
Make it equal to 0, right? Okay. So notice it's analogous, but not quite the same, of finding when the diver's height is 0. Here we want to find when the diver's velocity is 0. Okay. That is when the diver will reach the maximum height. So this gives us a much easier equation to solve, though, because remember, this formula was minus 32t plus 16. Set that to 0, and now let's solve that equation. It's going to come out exactly like you would expect it. So you just shift the the minus 32t back over to the right, and you get 16 is equal to 32t, or t is equal to 16 over 32. And no surprise, that turns out to be 1/2. Okay, so the diver reaches the maximum height after 1/2 second. So notice this is a parallel here that you want to pay attention to. Notice here we set the original function to 0 to find when the height was 0. Here we set the derivative function to 0 to find when the rate of change, right? In this case, the velocity is 0. And that turns out to be after 1/2 second. So so the diver goes up for 1/2 second, just very briefly, right? The diver goes up for 1/2 second and then starts coming back down again. That's because gravity is very powerful. So it doesn't take long at all for gravity to slow that diver down. Just 1/2 second is all, and then start bringing the diver back down to the water. How would we figure out then the diver's maximum height? So we know that that occurs after 1/2 second, right? So how do we determine exactly what that maximum height is? It's going to be a little bit more than 32, right? Because remember, the diver started at an initial height of 32. So, and the diver is going to go up for 1/2 second. So it's going to go a little bit above 32. How do we find out exactly how much above 32 that was? How do we figure out what the diver's maximum height was? Mohammed, can you tell me that now? Can you help me with that? Mohammed, are you still there? I want to check off people, so. Mohammed, are you there? Or are you just not answering me?
He was literally just here with his camera on, so that's weird.
What now?
He was literally just here with his
Yeah, no, he was just here a moment ago. All right, I'll switch now. Daniel, the other Daniel Gonzalez. Okay, so how can we determine when the not when, we know that it's after 1/2 second, but how can we determine what the maximum height of the diver is? You can type if you need to. You can chat if you need to. No, Daniel, not gonna respond. Okay, so what I'm clearly getting here are people who are logging on. Oh, all right, Mohammed, all right, you're back. But I think I'm getting people who are logging on and then checking out. Okay, so that's not a strategy for success. Okay, all right. If you're going to bother to log on, stay through the entire lecture, right? Okay, you'll just be that much better prepared for your homework and then ultimately for your test. All right. All right, Mohammed. Now that you're back, so let me ask you again. So we know the diver reaches the maximum height after 1/2 second. What is the diver's maximum height, Mohammed? So we just learned that the diver reached the maximum height after 1/2 second. So if I want to know what the maximum height is, how do I compute that? It's pretty easy. What do I do?
We just put in half second into the formula.
Right, you just put half second into the formula. See, just that easy, right? Okay.
Yep.
So see, not hard at all, right? Just take 1/2 and put it into the formula. And so whatever you get from that is what the maximum height will be. Someone may have to calculate this for me. Remember, put it into the original formula, right? Put it into the original formula because that's the height formula. Don't put it into the rate of change formula because that's the velocity formula, right? Okay, that's the rate of change formula. Let's see, this is minus 16 times 1/4. 1/2 squared is 1/4. So minus 16 times 1/4 is minus 4. And then plus 1/2 times 16 is 8. And then plus 32. So you see that works out to be 36, just a little bit more than 32, right? Because the diver didn't go up very long before he reached the maximum height and starts coming back down again. So the maximum height is 36. Again, don't take the 1/2 and plug it back into the rate of change formula because you're going to get 0. Right? Remember, we found that 1/2 was the solution to this equation, So if you calculate s prime of 1/2, you're going to get 0. You want to take the 1/2 and plug it back into the original height formula if you're looking for a height. Okay. All right. So so much for that example. I want to show y'all one more example here of finding the derivative using the limit definition. So this one's a little bit more challenging. So I'm going to do this one. The function is just a little bit tougher than previous examples that we've seen. Okay, but it works out nicely. So it's not a it doesn't end up being all that bad, but it starts off looking kind of rough. So again, what I'm trying to find is the formula for the rate of change or the derivative function. So I'm trying to find g prime of x, given that g of x is originally 1 over x minus 2. So what's a little bit tough about this one is the variable x is in the denominator. But we start off the same way, okay? So it's the limit as h approaches 0 of, it's going to be g of x plus h minus g of x over x plus h minus x. The only thing different here is the name of my function is g and not f. So I'm using g here instead of f, but otherwise, this limit definition looks like what we originally wrote down when we started doing this. All right, now let's see. Let's see if I can deal with the algebra here. So I have the limit as h approaches 0 of, what's g of x plus h? Well, I'm just going to take x plus h and plug it in to this formula, right, for x. So that comes out looking kind of ugly, though. I have 1 over x plus h minus 2. See, I just plugged the x plus h in to this x in the denominator, so you get 1 over x plus h minus 2 minus, and then g of x, well, that's just this formula. So that's 1 over x minus 2. And then in the bottom, I get, of course, x plus h minus x is just h. And see, this is what looks a little bit ugly now because we have this complex fraction. We have these two smaller fractions inside of this big fraction. And there's a question now at this point of how do I simplify this so that I can figure out what this limit is. Oh, by the way, let me point out something. I didn't stress this enough. Why can you, at this point, why can you not just immediately try to figure out what the limit is? Why can you just not immediately ask yourself, okay, I want to figure out what's happening to this expression as h goes to 0? So why do you have to go through any sort of simplification? Why can't you just go ahead and answer immediately at this point, you know, what's happening here as h goes to 0? Well, the answer is, look, as h goes to 0, this h is becoming 0. And what happens when you divide by 0? Can you divide by 0?
No, it's going to be undefined, right?
It's going to be undefined, right? So that's the problem with just stopping at this point and asking yourself, yeah, what's happening to this expression as h gets really small? Well, what's happening to this expression is you're dividing by 0. That's what's happening. And you don't know what happens when you divide by 0. So that's why we have to do a little bit of extra work here to keep simplifying this so we can better figure out what this limit actually is going to turn out to, be. Okay, let me show you what I'm going to do here. I'm going to subtract these two. I'm going to go ahead and in the numerator here, this h I'm just going to leave alone. But in the numerator here, I'm going to go ahead and combine these two fractions. So I'm going to subtract them. And to do that, you need a common denominator between these two fractions. That common denominator is going to turn out to be the product of these two denominators. So it's going to be x plus h minus 2 times x minus 2. All right, so what I have to do is build up these two fractions so they have this common denominator. Let me write that down. So I've got to change this fraction so it has this denominator, and I've got to change this fraction so that it has this denominator so we can, in this case, subtract the two fractions. All right, well, let's look at this first fraction first. What's missing from its denominator? It's missing x minus 2, right? It's already got the x plus h minus 2. It's missing this factor of x minus 2. So what I'm going to do is just multiply that into the top and the bottom of that first fraction. So here's what you get. You get x minus 2. I'm going to multiply that into the top and the bottom times 1. Multiply it into the top, and then let's also multiply it into the bottom. So I'm going to multiply x minus 2 into that denominator, which is x plus h minus 2. All of this is just the first fraction. Now, second fraction, what do I have to do? Well, you've already got the x minus 2, right? That's in this fraction's denominator. So you're missing this. So you have to multiply that into the top and the bottom. All right, so let's multiply it into the top. So I'm going to take the 1 and multiply it by x plus h minus 2. And then also multiply into the bottom. So I'm going to multiply the x plus h minus 2 into the bottom there. So I just multiply top and bottom by the same thing. Doesn't change the fraction, just makes it look different. And don't forget, this h is still here. Wow, okay? Now, at first, that looks kind of awful. But this is where you can't let yourself get intimidated by the algebra. All right, so we have the limit as h goes to 0. Let's see, what's this fraction? Well, what's this fraction? Just what it says it is. It's 1 times x minus 2, which is x minus 2, over x minus 2 times x plus h minus 2, minus, what's this fraction? Well, that's just 1 times x plus h minus 2 over this denominator, which is x minus 2 x plus h minus 2. Now you're in great shape. Now you can combine those two fractions because now, see, they have the same denominator. So, you know, you can add fractions with the same, or in this case, subtract fractions that have the same denominator, but you can't add or subtract fractions until they have the same denominator. So now we're in good shape. We can combine those two fractions. So let's see what happens. I get x minus 2 minus, because I'm subtracting all of this. So that's x plus h minus 2. Put it in parentheses because you're subtracting all of it. Now you can keep your common denominator, which is x minus 2 over x plus h minus 2. And don't forget, hanging along through all this process is this h down here. We're going to get rid of that in a minute, but not yet. Now, here's where good things start to happen. Look, you're subtracting this, right? So you can just remove the parentheses and change the signs. So I get x minus 2 minus x minus h plus 2 over this big ugly denominator here. And finally now, you get some cancellations. These x's go away, thank God. These 2's go away, and look what we're left with now. It's starting to look a little bit better. So I have the limit as h approaches 0 of minus h over all of this, x minus 2 over x plus h minus 2, and then I still have this h. But look, dividing by h is the same as multiplying by what? Okay, so think back to your arithmetic. When you divide, that's the same as multiplying by what? See, if I divide a number by 2, for instance,
Reciprocal?
that it's the same as multiplying by the reciprocal, right? So x divided by the 2 is the same as x times 1/2, correct? That's the same thing that's going on here, Colin. Here we're dividing by h, so that's the same as multiplying, Colin, by what? Dividing by h is the same as multiplying by what?
1 over h.
1 over h. And that's a real important observation. Of course, it comes from grade school, but it's still useful in college. Dividing by h is the same as multiplying by 1 over h. So instead of writing this as this big fraction divided by h, I'm going to write it as this big fraction times 1 over h. And Colin, that's really useful because what happens to these h's now?
Now they cancel each other out, but be careful, there's a negative sign on.
Yeah, but you keep the minus sign. That's right. Okay. Yeah. So the h's cancel, and now we're left with this minus 1 over x minus 2 times x plus h minus 2. Now, okay, wow, all right. So I had all that work, and I still have this big mess, and I still have to take this limit. But what I claim is now we're in great shape, Colin. You can see the answer. What's going to happen, Colin, to this expression as h goes to 0? What are you going to get left with?
Well, I first want to talk about how in the denominator there's an h that goes to 0, right?
Right. See, there's no h here, so nothing happens here, right? There's no h here, so nothing happens here. This x minus 2 is going to stay the same. The only place you have an h is right there. And so what happens there when h goes to 0?
Well, then the x plus h minus 2 becomes x minus 2.
Right. You said it. So look, all you're left with now is minus 1 over x minus 2 times x minus 2. See, the h goes away. I guess that's better known as minus 1 over x minus 2 squared. There, we're done. That is the result. See, the h's are gone now, right? So there's our answer. I forgot what the question was. Oh, yeah. It was, what is the derivative of this function? So now we know it. We know what the rate of change function is, or the derivative function is. It is minus 1 over x minus 2 squared. Didn't come out that bad, see? But it did take a little bit of work to find it, okay? But the actual answer is not that bad. Now, see, you can use that formula to answer all sorts of questions. All the hard work has been done. And now all the questions are real easy to answer. So for instance, if I want to know what is g prime of 1, what is g prime of 1, just to get an easy number to work with, I would get -1 over 1 minus 2 squared. Notice that's going to come out to be -1 over +1, which is -1. So what is that telling me? What is that telling me about the original function g? The fact that g prime of 1 is -1. What does that tell me? Well, what's happening to this function at 1? Is it increasing or is it decreasing? So if you were to make the graph, we can't see the graph. Don't know what the graph of this looks like, maybe, but we really don't need the graph. I already know at 1, is the curve going up or is the curve going down? Calvin, are you there?
Yes, sir. What was the question?
Yeah. So for this function g, see, I know its rate of change function, and I calculated g prime of 1 using that rate of change function. I calculated g prime of 1 is -1. So I just chose the number 1 at random, but I know something now about the curve. Even though, see, Calvin, even though I don't have a graph of the curve, I know something about it. Is the curve going up at 1 or is the curve going down at 1?
Going down.
It's going down because the rate of change is
Negative.
Negative. That's right. Okay. The rate of change is negative. And I even know how fast it's going down. It's going down at this rate, right? -1. The slope of the tangent line is -1. What about at 0? Is it going up at 0 or is it going down at 0? Is it increasing at 0 or is it decreasing at 0? So you can answer that just by computing g prime of 0 from your formula. So that would be -1 over 0 minus 2 squared. That looks like that's going to be -1/4. That's still negative, right? That's still negative. So at 0, the curve is still decreasing. Okay. Yay. So Calvin, and I want to make sure I mark when people answer questions for me. Let's actually make I actually have the graph of this one, so we can look at it really quickly. Let's see if I can get back to it fast. So there it is. Can you all see that? There's the graph of 1 over, there's the graph of 1 over x minus 2. And so that's the blue curve. And I drew a tangent line in here. So there you are. There's at 1, right? Okay. And indeed, see, the curve is decreasing at, the curve is decreasing there at 1, right? And it's also decreasing at 0. In fact, it's decreasing at a lot of places, right? Okay, from left to right, okay? But we don't have to worry about drawing tangent lines and going through that lengthy process now to find the rate of change anymore, because now we have the formula for the rate of change. So we can find the rate of change at any input that we like now very easily, just by using that nifty formula that we have, -1 over x minus 2 squared. Okay, all right, so now that we've done all of that work, okay, we're as I promised, now we're going to find some shortcuts. So I'm going to show you now some easy rules that you can use for finding derivative functions, rate of change functions, but you don't have to go through all of this limit process. Okay, all right. So people have worked very hard to find very nice rules that we can use to find rate of change functions, derivative functions, where we don't have to go through this limit definition process, because that's very clumsy and cumbersome, right? All right. So we're going to take up now what those nice shortcut rules are. But let's take a break here for a few minutes, okay? For 5 or 6 minutes here or so. So I'll be back at, let's say, well, let's come back at 12:45, because we can go through the rules pretty fast. So we'll come back at 12:45 and we'll start with that set of notes. All right. So I'll see y'all in just a few minutes here. Let me pause the recording. Okay, so let's resume now, and let's make our lives a little bit easier. That's always good, right? So I'm going to show you now a series of again, rules that will make it easier, much easier now for us to find derivative functions. And then once it becomes easy for us to find derivative functions, then we can really learn better about how we can apply derivative functions to answer practical questions for us, right? So it won't always be consumed with trying to find a derivative function, but once it becomes easy to find derivative functions, then we can really instead concentrate on using derivative functions to help us answer the sorts of questions that they're great at, okay? So let's start with the easiest rule of all. Actually, all these initial rules are really simple, and this is called the constant rule. And so the constant rule says, I've got it here expressed in notational terms, but I will then say that again in a little bit more standard language, a little bit more everyday language. So the constant rule says that if you have a function whose formula is a constant, so a very simple function like that, a formula whose function is just a number, whose formula is just a number, just a constant, then the rate of change of such a function is 0. Okay, and so here's an easy way of stating that rule. If you want to say it in words and not in symbolic terms, it just says the derivative of a constant or the derivative of a constant function is 0. It's very easy to see why this is true. So this is not a mysterious rule at all. If you have a constant function, right, and you make a graph of that, you get just a horizontal line like this, right? The graph of a constant function is going to be a horizontal line. So the graph of f of x equals c, where c is any constant, will just be a horizontal line. And obviously the rate of change of a horizontal line is 0, right? Okay, horizontal lines are not going up, they're not going down. So their rate of change is always 0. So this is easy to deduce. There's nothing mysterious about this so-called constant rule. But it is useful because we will apply it lots. All right, so rate of change of just a number, just a constant, is 0. Okay, now the second rule is going to be much more important to us. All right, and this is called the power rule. We're going to see a couple of different versions of the power rule. I'm starting with the simplest version of the power rule, and then a little bit later we're going to look at a generalization of the power rule, which is more powerful. And this rule is really ubiquitous in calculus. We use it, either this rule or its more powerful generalized version. We use it all the time in calculus for lots of reasons. So you're going to really become very accustomed to this particular rule. So here's what the power rule says. If you have a function that is a power, okay, in this case I wrote a power of x, but it could be a power of whatever your input variable is, right? So if you just have it as your input variable raised to a power, all right, then the power rule tells you how to take the derivative. Okay, I do want to point out, though, before I look at the actual power rule itself, this exponent in the power can be any number at all. It can be a positive number, it can be a negative number, and it does not have to be a whole number. So that makes the power rule really powerful. All right, this exponent can be negative, it can be positive, it can be a fraction as well, and the power rule will still apply. The only restriction on this exponent is it cannot be 0, and in a moment we'll see that doesn't make any difference because we don't need the power rule if the exponent is 0. Okay, all right, so for any exponent at all, here's what the power rule says. Here's how you take the rate of change function. Here's how you take the derivative. Okay, what you do is just simple. You bring the exponent down, right, as a coefficient in front, and then you subtract 1 from that exponent and leave that as an exponent. All right, so you get that process. Bring this down and subtract 1. That's how you find the derivative function of a function that is a power. Okay, all right, trust me, we're going to do that process a lot, okay? Both the process itself, and we'll also do a lot the opposite of that process for strange reasons, okay? That we'll learn about later. So the power rule, we're going to use that virtually every day, all right? All right, now let's look at just a couple more rules, and then we'll practice with some examples, all right? The next rule looks, it's called the constant multiple rule. It looks kind of complicated when you write it out symbolically, okay? But it's much easier when you say it in words, all right? So what the constant multiple rule says is that if you have a function and your function is formed by taking a constant times an expression. So remember, a constant is just a number, right? So if you have a function that's a number times an expression, so this expression can involve x, but the constant is just a number. Then here's how you find the derivative. All you do is you just keep the constant and then you take the derivative of the expression. So the constant multiple rule sort of says that when you're finding derivatives, constants are, you can kind of ignore them, all right? The constants really don't contribute, or you really don't have to think about them in the derivative. They stay the same in the derivative, okay? So again, let me sort of repeat that. If you have a function that's a number times an expression, the expression can be complicated, then the derivative is you're just going to keep the number and then just worry about taking the derivative of the expression. So you don't have to do anything with the constant. You can just sort of leave it alone. I hate to say ignore it because it doesn't go away, but you can just leave it alone, all right? Again, we're going to look at examples of all of these things, okay? One last rule before we start looking at examples, really nice, easy rule. This is called the sum rule, all right? So again, when you see it written out symbolically, it looks complicated. But when you explain it in words, it's not complicated at all. Here's the verbal version of the sum rule. If you take the derivative of a sum, not a product, because that's going to be different. But if you take the derivative of a sum, that is just the sum of the derivatives. So in other words, if you have derivative of a sum, it can be a difference too. You can have a plus or minus here. Then just take the derivatives of each of the terms separately. So if you're taking the derivative of a sum, something that's an expression plus a second expression, just take the derivatives of the two expressions separately. So a derivative of sum is the sum of the derivatives. Very easy rule. Very nice rule, okay? All right, well, let's think about, so we had what, 3 rules there or 4 rules? Let's think about applying those 4 rules, and I'll show you how fast it is now to find derivatives without having to use that horrible limit definition, okay? All right, so let's look at some examples. So here's what we're going to do. We're just going to differentiate each one of these functions. In other words, I'm going to find the derivative of each one of these functions, but now I can do it really quickly. So what is the derivative of minus 12 going to be? Notice that is a constant, right? Because this expression doesn't have x in it. So what is the derivative of that function? Just really fast, what's that going to be? Mr. Gonzalez, did you come back? Are you back? Can you answer that, what the derivative of that function minus 12 is? Still not back? Lance, can you answer me that? What is the derivative of minus 12?
Yeah.
Yeah.
Wait, since it doesn't have anything attached to it, wouldn't it just be 0?
That's right, 0. Yeah, okay. Yeah, you're very hesitant there, but don't have to hesitate. That is going to be 0, yeah, because that's a constant.
Okay.
Because it doesn't have the variable x, right? Okay, so
yes.
The derivative of that is very easy. That's 0. Okay. Usually we like it when derivatives are 0. That makes our life easier. And here's one case where that's true. All right. So see very fast, derivative of a constant is 0. All right, let's look at this next one. All right, so here's g of x is pi plus x. I tried to make you think this was complicated because I put pi in here. All right. But please remember, pi is a constant, all right? So that's the most famous constant in mathematics, maybe after 0 or 1, all right? And so that is just a constant. One other thing to notice here, though, is this is a sum, okay? This is a sum. So remember, the sum rule is going to be involved here as well, all right? So how do we find the derivative of this? Well, remember, the derivative of a sum is the sum of the derivatives. So you can take the derivative of the pi and the x separately. You just go one term at a time when you're finding the derivative of a sum. What is the derivative of pi going to be, however? So that's a constant. So what is its derivative?
It's just 0.
0, right? Yeah, its derivative is 0. So we got that done. That's fast. That is 0. And now we have to worry about the derivative of, what is the derivative of x? Okay, now here's where the power rule is going to come into play, because x is a power. It's x to the, you don't see it there, but that's x to the first power. So that means that we can use the power rule to find the derivative of this term. The power rule says, okay, I find the derivative by bringing the exponent down as a coefficient. So I have 1 times x and then subtract 1 from the exponent. So I get 1 minus 1. I'm going to not write this 0 now. I don't have to write this 1 in front. So what I really have here is x to the 0th power. But what's x to the 0th power? What's any quantity to the 0th power other than 0?
1.
1. Ah, so that's cool. The derivative here just turns out to be 1. Notice the derivative is a constant, okay? That's not mysterious at all, because what sort of function is g? If you make a graph of g, what sort of picture will you get? Remember, the original g was pi plus x. So when you graph pi plus x, what sort of function is that?
A line?
That is a line, yeah. Donna, that's a line. And what's its slope? What's the slope here of this line?
1.
1, yeah, okay. The slope is 1. Well, you know, lines have a steady rate of change, right? And their steady rate of change is the same as their slope. So not surprisingly, when we applied our derivative rules, we ended up with 1, which is the slope of this linear function, right? But it had to turn out that way, or that means something was amiss, right? Okay, so we could have figured out what the rate of change was here just by noticing that this is a straight line. But if you didn't notice it's a straight line, that's fine. Your derivative rules tell you the same thing. The rate of change here is, the rate of change function here is 1. Well, here's one of the most famous functions in mathematics. This is x squared, right? What could be more important than that function, right? And so now we want to find the rate of change. I'm going to call that, since I didn't give a name for this function, I just have the variable y. When I'm writing down the rate of change, I'm going to write down in old-fashioned notation dy over dx, but that means same thing as the prime notation. That is just the derivative function. So what will my derivative function here be of x squared? This is going to be the power rule, because x squared is a power, right? Okay, it's the power of 2. So what does the power rule say my derivative is going to be? So this is what you have to memorize, right? But it's a very simple rule. Bring the 2 down in front as a coefficient, and then subtract 1 from the exponent. So you get 2x. So the rate of change function, the derivative function for x squared, is 2x. So that's interesting to know, right? The derivative of x squared is 2x. Now, when we first look at this example, we're thinking, I don't remember any rule that involves square roots. So how do I find the rate of change function for the square root of x? Another one of our most famous functions in math, right? Square root of x. So how do I find its rate of change function? Because none of those rules seem to apply here. But okay, here is, whoops. Here now is something that's very important in calculus. You learn about this a lot in algebra, but you're always wondering in algebra why this is useful. But now you're going to see why it's useful. Here I have square root of x written using a radical. You know, like we would in, you know, middle school, right? I'm writing square root of x using my square root sign. But when we get to high school, right, and learn more about algebra, we learn that, oh, you don't have to write square root of x using a radical. You can also write that as a power, right? You can write that using an exponent. Square root of x is the same as x to what power?
Half?
So how do we convert a radical to a power? Someone recall that for me? It's always easy to forget this because it's not intuitively obvious, but it's an important thing to remember. Well, you're going to learn why it's important to remember right now.
Isn't it to the power of 1/2?
It's power of 1/2, right? That's right, Lance. Yeah. Square root of x is the same as x to the 1/2 power. Now, when you're learning that in algebra, you're always thinking, okay, that's all right, great. Why do I care, right? That square root, you know, why do I want to rewrite square root of x as x to the 1/2 power? Well, here's one of the key reasons. Because once you have square root of x written as a power, right, not as a radical, but as a power, then when you want to find the derivative, the rate of change of this function, now you can use the power rule. So the power rule tells me that the derivative of x to the 1/2 power, Lance, would be what?
X to the 1/2 power is the derivative.
Yeah, the
Would
power
it be
rule says
would it be 1/2 x to the power of negative 1/2?
exactly right. So you bring the 1/2 down, right, as a coefficient. So you have 1/2 x to the 1/2 minus 1. So you have 1/2 x to the minus 1/2. Cool. There is the derivative function for square root of x. Now, I'm going to rewrite this now back in square root notation. All right. Since the original function started in square root notation, let's convert this back to square root notation. So let's see, this is 1/2 times. Now, when you have a negative exponent, remember, negative exponent means take the reciprocal. So x to the minus 1/2 is 1 over x to the 1/2, correct? Negative exponent means take the reciprocal. So I didn't write that very well, but that's in the denominator there, that's 1/2. And now remember, x to the 1/2 is square root, right? So you have 1/2 times 1 over square root of x. And now you can multiply these two fractions together. So you get 1 over 2 times square root of x. Neat. There it is. The derivative of the square root function, interestingly enough, also involves the square root, but maybe not like what you would think. The derivative of square root of x is 1 over 2 times square root of x.
Sorry, I have a
But
question.
rewriting that radical as a fractional exponent, that was really the key, right? in allowing us to find the derivative function. Yeah, did someone have a question? Donna, did you have a question?
Yes, I did. Wait, how did you change the half to a 2?
How did I change the half to a 2? And where at?
Before,
Here?
no. If
Here?
you keep going the next step, next step.
Here?
No, next one.
One
Yeah,
half times, yeah.
right on it.
Yeah, I didn't change this 1/2 to a 2.
No,
I-
the one before it, the one that comes.
Here?
No, you were at the right thing.
Here?
No.
Or here?
Yeah, right there. Where you see 1/2 root x.
Yeah.
Yeah. How did that was a half before. That 2 was a half. How did it become a 2?
Because I had two separate fractions here. So I had 1/2 times 1 over square root of x. So how do you multiply fractions? You multiply their numerators. So I multiplied 1 times 1, that's 1. And then I multiplied 2 times square root of x. So that's just 2 times square root of x.
Oh, okay.
Yeah, I
Okay.
combined the two fractions into one.
Got you. Okay.
Yeah.
Thank-
Okay. All right, so there's the final derivative function. All right, let's try this one. X to the -3, x to the -3 power. That happens to be, we know from exponents, x to the -3 means 1 over x cubed, right? Because negative exponent means you take the reciprocal. But I really don't even care about that, because all I'm asked to find here is the derivative, right? And remember, this is a power. -3 is a power, just like 1/2 is a power here. So you can apply the power rule. The power rule works for any exponent except 0. So you don't have to worry that x to the -3 x to the -3 means 1 over x cubed. You can go ahead and find the derivative immediately by taking the -3 down and then subtracting 1 from the -3. So you get -3x to the -4 power. That's it. Okay, that's it. There's your answer. That's the rate of change of x to the -3. So unless you're asked for something else, you don't have to do anything else here. All right, so how about this function, 5 over x squared? Well, this is not quite a power because the x squared is in the denominator here. But we can turn this into a power really easily by moving the x squared out of the denominator up. So when you do that, you have to change the sign of the exponent. So 5 over x squared means 5 times x to the -2 power. So get this x out of the denominator first by changing the sign of the exponent. Now you can find the rate of change function just by using the power rule. So you cannot use the power rule here, but you can use the power rule when you bring the x squared up to the numerator. So let's see, what's the answer going to be? Bring the -2 in front. So you have -2 times 5 to the x -2 minus, subtract 1 from the exponent. Let's see, -2 times 5 is -10. And then we have x to the -3. Now, because my original expression did not have a negative exponent in it, I'm going to change my answer so that it does not have a negative exponent. So I want my answer to look like my original expression. Well, how do you fix x to the -3 so it doesn't have a negative exponent? You simply bring it back to the denominator. X to the -3 means 1 over x cubed. So there's your answer Interesting answer. So the derivative of 5 over x squared is minus 10 over x cubed. Notice the sign change there. Now, here's what mistakes you're going to want to make. So you've got to caution yourself to prevent these mistakes. When students are looking at this formula and thinking about the derivative, they want to apply the power rule too quickly. So they think, the derivative of 5 over x squared, that should be 5 over 2x, because I'm going to bring the 2 down here and subtract 1, which gives me x to the first power. So students will write this as the answer, but that is not the answer, because this is not quite a power. You have to write it as 5 times x to the minus 2 first, before you can apply the power rule. By the way, the other rule that we applied here was the constant multiple rule. Notice we have 5 times x to the minus 2 power. That wasn't just x to the minus 2 power. But remember, the constant multiple rule says if you're multiplying by a constant, you can just keep the constant. Don't worry about taking the derivative of the constant. So I just kept the 5 here all the way through the problem. Let's quickly do one more. I think I've got one. Well, I've got 2 more, but let's do this one really fast. Okay. All right. So I want to find this function 1 over 5 cube root. That's cube root of x. Wow. How would I do that? First, change the cube root in the denominator to a power. The cube root of x is the same as x to what power? Remember that? What's square root was x to the 1/2 power. What about cube root of x? What power would that be? Do y'all remember? It's 1/3 power. Yeah. So cube root of x is x to the 1/3 power. All right. So that's step 1. Get rid of the radical. Write this as x to the 1/3 power. Now, I don't want the x in the denominator because I want to use the power rule. I got to get this x out of the denominator. Don't worry about the 5. It's just the x we have to move out of the denominator. So that would be, I'm going to leave the 5 in the denominator, but I'm going to bring the x to the 1/3 power up. So that gives me x to the minus 1/3 power. Now you can apply the power rule. So the derivative is going to be, bring the minus 1/3 down. Going to multiply it times the 1/5 that's left in front here, and then times x to the minus 1/3 minus 1. So let's see, I get minus 1/15 x to the minus 4/3. Minus 1/3 minus 1 is minus 4/3. Let's see, now I'm going to bring that x back down. So I have minus 1 over 15 x to the positive 4/3 power. And now I'm going to convert the 4/3 back to a radical. So that would be minus 1 over 15. Since we have a thirds here, that's going to be cube root. And then the 4 will stay as an exponent. So there's my answer. Minus 1 over 15 cube root of x to the 4th power. You can actually simplify this a little bit more, but slightly, but it's not really that important. So I'm going to stop right there for right now because we've run out of time. Okay, well, we still have some more examples to do, a few more examples to do here, but we'll using the same rules, but we'll take those up. Next time. So remember that the test answers are posted, right? The test answers are posted, and then sometime tomorrow I will email you back your graded test, right? And I will put the grades into ReviSign. So y'all can be looking forward to that sometime on Wednesday. So remember, there's one easy homework that's due tonight, right? Okay. Finish up that homework that's due for this evening. Well, okay, so we're done now. So we'll stop right there. And I will see you again on Thursday. That'll be our last lecture before spring break, right? So we get a little break. So hang in there till Thursday. And so you can have your spring break week off.